Respected Principal Dr. P. Nasir, our Chief Guest of the day, Dr. Arijit Mallick, and dear participants, a very good morning to one and all. Really, I am very happy to welcome you all to this international webinar organized by Department of Chemistry in association with the IQAC, Mannaniya College of Arts and Science, Pangode. Today, we are proud to have an eminent scholar and JSPS Fellow of Kyushu University, Japan, Dr. Arijit Mallick with us to deliver a speech on carbon dioxide capture from air to control pollution and gas purification. In spite of his tight schedule, he accepted our invitation and joined with us to share his valuable information. I hope that all of you will have a stimulating experience today. So I have been privileged here to extend a hearty welcome to you, sir, on behalf of Department of Chemistry, IQAC and Mannaniya College for delivering the speech. Now I would like to welcome Dr. P. Nasir, Principal and former Director of Minority Welfare Department, Government of Kerala. Actually, he is the person who gives us inspiration and encouragement for organizing this webinar. So, on behalf of Department of Chemistry and IQAC, I extend a cordial welcome to you, sir, for inaugurating the webinar. Now, I am delighted to offer a hearty welcome to all the participants, especially faculties, scientists, scholars, and students from various institutions, departments, and universities who are anxiously waiting for today's webinar. Finally, I welcome all my colleagues, alumni, and students of our college to this webinar. Once again, I welcome you all to this webinar and hope that you will have very exciting and enriching session. Thank you. Now I am handing over the mic to Dr. P. Nasir, Principal, Mannaniya College of Arts and Science, for inaugurating the webinar.
Thank you, Professor. Good morning, everybody. Warm greetings from Mannaniya College of Arts and Science. Today is our distinguished guest, Dr. Arijit Mallick, my dear colleague and HOD, Department of Chemistry, Dr. Mercy Raj, my dear colleagues and fellow participants. Really, I am very proud to be here to inaugurate this international webinar organized by the Department of Chemistry on behalf of IQAC, Mannaniya College of Arts and Science. As you have been seen here, Mannaniya College of Arts and Science is an aided minority college having status of national minority institution of National Commission for Minorities Education in India and affiliated to the University of Kerala. Friends, our college has been recently accredited by National Assessment and Accreditation Council. Followed by this accreditation, we had planned a lot of academic and extracurricular programs to excel our institution far with other premier institutions in the country, mainly this academic year. Unfortunately, thanks to the COVID epidemic across the world, the scenario has been adversely affected us. However, we have been switched over to conduct many webinar series on various subjects. As part of this, we conducted many webinars in national level. But this is the first of its kind as an international webinar entitled CO2 capture from air to control pollution and gas purification. This is one of the most relevant topics and highly useful to our common society as well as the academic community. I think the talk of our prestigious resource person, Dr. Arijit Mallick, will enlighten us to a large extent. The participants are hereby requested that to be involved much more serious discourses followed by his deliverance. At this juncture, I proudly declare that this international webinar has been inaugurated with your kind permission. Thank you once again, all of you. Thank you.
I'm Siat, Assistant Professor, Department of Chemistry, Mannaniya College of Arts and Science, and I'm the program coordinator of this international webinar. And here is my duty to introduce our chief guest, Dr. Arijit Mallick. Dr. Arijit Mallick is currently working as a JSPS fellow in the Kyushu University, Japan. Before joining the Kyushu University, he was the postdoctoral fellow at the King Abdullah University of Science and Technology, Saudi Arabia, with Professor Mohammad Eddaoudi. And he finished his PhD from Academy of Scientific and Innovative Research, CSIR-NCL Pune, with Dr. Rahul Banerjee. He was the recent Shanti Swarup Bhatnagar Prize winner. Now, Dr. Mallik focuses his research mainly on inorganic and material chemistry. His expertise is in synthesis, characterization of metal organic framework, and their application in the area of proton conduction, gas absorption, direct encapsulations and release, the chemical sensing and catalytic performance, and other electrochemical application. He has number of patents and publications, and his articles are published in high impact international journal. So now I invite Dr. Arijit Mallick to take on the stage, and we welcome you to give a good presentation to our audience. Thank you, Arijit. Please take the mic.
Good morning, everyone. I think it's a good morning to you. It's good afternoon here. It's around 2 p.m. here. So I would like to thank everyone who joined this webinar. And also I want to thank the Mannaniya College of Arts and Science to give me opportunity to deliver their talk. So I'll share my screen so that we can start the presentation. So can you?
Yes, now.
Yes. So it's fine. Everybody can see.
Fine.
So today I'll talk about myself. I am Dr. Arijit Mallick. I'm working at Kyushu University. You can see the university campus shown in that picture in the front. It's a very green, nice campus. And today I'll talk about the CO2 capture from air to control pollution and gas purification. Initially, I thought that I'll give a complete scientific lecture. Then I thought about the viewers from all different areas. I made a somewhat general talk, and I think everybody will like it. Let's go. So the content of my slides are based on the 4 main major questions, and I will discuss on and try to answer these questions. The question 1 is air pollution new in this earth? So I'll talk about how the air pollution happens in this earth and how the creatures are affected by this air pollution. And what is the contribution of human in air pollution? And what we are doing to solve this problem, like we are scientific community, what we are actually doing to solve this problem. And at last, what you can do, what can you do to solve in our daily life, what the general people can do to solve this problem. So to answer this question, is air pollution new in this earth? I'll go back to the 5 to 4.5 billion years ago when the earth was a ball of fire and the temperature of the earth was around 2000 degrees Celsius. So no living being can stay there. So at around 3.5 billion years ago, so there was a huge change. So you can see the first living being come to the earth. That was a one-cell bacteria. And these one-cell bacteria do photosynthesis in presence of light and generates oxygen. So before that, on our earth, there was only carbon dioxide, nitrogen, and some water vapor. And these one-cell bacteria started making colonies and started producing a lot of oxygen in the air. And that is the initial source of oxygen for living being. And after that, for billion of years, they are just generating oxygen, and this oxygen forms a layer on top of our earth, and in presence of the sunlight, that oxygen do reaction and form the ozone, O3. These ozones are actually makes a protecting layer on top of the earth's surface. And that's why the living being on the land can survive. In the water, the creature can survive, but in land, we need a protecting layer to save us from the ultraviolet ray of sun. So the ozone layer actually do that work. So at around 200 million years ago, the dinosaurs come in planet. They evolve, and these they dominated this planet around 150 million years. So they are the highest long-lived creature in this planet, and they were very, very high, gigantic figure. The giant animals at that time was there. Why? Because the oxygen level in the earth was too high that can provide that level of oxygen, the giant creatures. And then a event happened around 65 million years ago. A big asteroids hit the Gulf of Mexico, and the whole earth became restless, and thousands of volcanoes came out, and the earth where there was a release of oxygen and so many creature was there, everything died due to the air pollution. At that time, the temperature of the surface become 500 degrees Celsius. Nothing can live in this bad atmosphere. And then again with time, everything settled down, and the human evolves at around 3.5 million years ago. And at around 2 to 1.7 million years ago, they started using fire. And they are the ancient human, they called the Homo erectus. And this, the time when humans started using the fire, the humans started their contribution to the air pollution in this earth. So now I'll come to that, what is the contribution of human for this air pollution? So at around 70,000 years ago, Homo sapiens, the modern human, evolved. And around 10,000 years ago, they discovered the wheel. So when the knowledge of wheel and the knowledge of fire come together, slowly, human developed the machine. And this machine is started the more and more pollution in this planet. So with time, people started civilization, industry, and they started burning coals. So before 1950, that people are the main source of fire, people are using the coal. So for industry, they are running with the burning coals. And this coal burning creates a lot of air pollution. So at around 1661, the first person who make people concerned about air pollution was John Elvin. He wrote a book, Fumifugium, who describes the smoke of London. At that time, he describes that how this polluted air affects the human health, but nobody was aware, nobody taken this point seriously. In the year of 1770 to in between 1840, that was the time of the Industrial Revolution. At that time, James Watt make the steam engine, and all the industry pop up, and that they are growing so fast around the Europe. And these cities are now full of smoke, especially the main cities in Europe like London, where the smoke, the black smoke was covered all over the cities. And at that time, people used to say that this smoke is the sign of prosperity and economic growth. But they don't understand that this smoke is killing them. And when they understand, in 1951, in a single day, 7,000 people died in London in one part of the city. So what happened on that day, that the wind flow stopped, and the thousand of chimneys, the smoke come out and cover whole area, and people cannot breathe and cannot see even 10 meters. And after that, at that time, they checked the CO2 and SO2 level of the atmosphere increased so high, people cannot breathe and they die. And then in 1958 or 1961, they made an act that the industry should be far from the cities or locality, so that the smoke come out from the industry should not affect the human life. And in around year of 1960, the people started the natural gases and petrol and diesel. And this use of natural gas instead of the coal, that reduced the pollution for that time. So there is around 60% drop of the air pollution happens during that time. But recent years, the recent decades, again the pollution predominant, and it is reached to a very high level. So we need to, times come here to think about how to control this pollution. Otherwise, our future will be similar like the dinosaurs and other creature extinct from our earth. So what is the WHO organization, the World Health Organization? They publish some data, and they said that air pollution is the silent killer. It's not only affect our lung, it also affect the heart, it regulate the heart diseases, brain stroke, and all type of cancer. And 7 million of people are dying every year due to air pollution. And especially the Asia, Southern Asia, like the India, China, these parts are the most populated areas. And the WHO data is saying that 80% of the world population are living in urban, not in the village. And the urban area, the air pollution is the air quality is 10% bad than the normal limit. So we need to think about how to solve this thing. And if we think about, we see the situation in India. So this is the first, it's showing the air quality map of India, and especially northern part of our India, like starting from Delhi, Punjab to up to Bihar to West Bengal. This northern part air quality is the worst. But it is not only affect the northern part, it is affecting all over the India. So if we see the 2019 data, the most polluted city in this world, out of 30, 21 from India. So in India, most of the cities are very, very much polluted. And 140 million people in India are breathing air, which is 10 times or more bad according to the safe air quality limit. And around 2 million people every year is dying due to the air pollution. And if we see the air quality index, if the air quality index is good, if it is 0 to 50 microgram per meter cube area. But if when this particle matters increase up to 500, it's like a gas chamber. And if you cannot believe, during the night of Diwali, at that time the people in India start do the fireworks, and the air quality index reach up to more than 1,000. So 500 is hazardous, and the air quality index reached to 1,000. So you can believe that we are inhaling the air, which is as bad as taking 50 cigarettes in a day. So we need to control about it, put a control over it. And if we see the source of air pollution in India, it's coming due to 45% are coming from the construction and dust. And why it has happened, last few decades, India faces the growth, and this fastest growth make a huge construction over all cities. And these construction are not according to the air pollution management system. So it's highly polluting our cities and all over the India. And also 17% is coming from the waste burning. So especially the farmers, they want to burn the crop after one session of farming, and that creates a lot of pollution. So not only in cities, in village areas as well. So, and not only that, the number of vehicle, the transportation vehicle in India increase a lot. If you think about in Delhi, so in a single day, around 1,500 new vehicles come to the road. So you can imagine, so such a huge amount of the transportation vehicle is creating a lot of pollution in our common society. And here you can see a simple image. So recently, due to the COVID-19 situation, the air pollution level all over the world is reduces, and it is showing that this is the low quality, the air quality improved around last 20 years. This is the minimum air pollution happens. And you can see this image of Delhi. So that was the before COVID-19, though it is full of smoke. So during COVID-19, it's become clear. So if we stop our activity, we can actually control this pollution. But now we need to think about, and we need to do these things. So what is the pollution happens in Kerala? So if you see in 2017 that a big cyclone came and a lot of people died and missing. 2018, huge flood and a lot of people died. So in Times of India, they put a very nice image where they are saying that Kerala may be the God's own country, but it is the country of our people as well. We need to think that the deforestation and construction, that is the main reason of this landslide and this huge, the natural calamity. So we need to now think, otherwise what will happen? So what will happen actually, the future prediction says that already as compared to 1984 to nowadays, this is the data up to 2016, the polar glacier is melting, and some of the from the glacier, the storage methane is coming out. You can see the scientists are doing the experiment. The ice is burning because of the methane, and this methane are the 20 to 50 times more dangerous than CO2. If it will mix with our atmosphere, it will be unbearable situation. And this ice, the glacier melting, not only affecting the polar part, it will increase the water level of the sea, and that will make flood to the sea level, all areas. And due to the increase in temperature, the droughts will happen, and there will be no farming. And one more thing is that there is a hole in the ozone sphere. The industry are producing carbon dioxide, sulfur dioxide, and nitrogen oxide, and that makes the thickening, the weakening of they are making very hole in the ozone sphere, and the ozone layer is becoming very thin day by day. And their quality, the performance of stopping the ultraviolet ray from the sun, it's reducing. So human will face different bad diseases due to this the problem. And another bad thing can happen, that the sea water temperature, if it's increased 4 or 5 degrees more, there is a below of the water level, there is a huge tank of methane, which is due to the dead fish and other animals. So if the temperature of the sea increase, the methane will come up from the sea, and that time no creature will live in this world. So people should be careful what we can do to stop this air pollution. So what we can do, what we are doing, scientists and scientific communities. So people are trying to capture this CO2, SO2, and the greenhouse gases in the using different technologies. So what is the present technology in the industry are using? They are using liquid amine. This liquid amine react reversibly with carbon dioxide, and then they capture this carbon dioxide, and they then they transport it in different way and use for different other application. But this is pretty cheap. They around $66 per ton of carbon dioxide capture. But it is also reversible, as I told. But there is some problem. Problem is that these amines are toxic and corrosive. So if you mishandle it, and it's hamper our biological system, and also it can damage the container or instruments. So these amines are not good for our health. And also that it's require high amount of energy to release this gas. So we can capture this gas by amines, but when we are going to release it, we need to use a lot of energy. So scientists are thinking some alternative ways to do that. So what we are doing, we use metal organic framework. So what is metal organic framework? I'll introduce you guys. So metal organic frameworks are a crystalline powder, porous material. So if you see in normal ice, it will be like salt or sugar we use in daily life. It's similar like that. But if you see in microscope, you can see it's a crystalline, well-shaped, nice particles. And if you see more deep in molecular level, they are framework, porous framework. It's like a sponge, porous sponge, but it is in molecular level. And it can actually capture these poisonous gases like CO2, SO2. And how it forms? So the metal ion, and this is the metal ion, and this is organic linker. You can see benzene dicarboxylic acid. And they are self-assembled, and forms this three-dimensional structure. And how they work. So if you see this, it's video, it's working or not. So here you'll see that carbon dioxide come out from the chimneys can be stored in this metal organic framework, and then that can be used for other purpose. And here the MOF, the important part of that, what I told previously, the problem we were facing with the liquid amine, they are toxic, but MOF is not toxic. You can handle it in huge amount, and there is no chemical reaction happens with CO2 and MOF. They are physically adsorbed. So the carbon dioxide just sit inside the MOF pores, and it can be stored or separate. And so then after storing, what we will do that carbon dioxide? So there is some catalyst that use this carbon dioxide to convert it to some useful chemicals, which can be used for energy generation or some other purpose, which is useful chemicals. So what MOF is doing to store, it can store or it can do the separation. So that carbon dioxide or any gases can store in this porous framework, or it can selectively take the poisonous gases like CO2, but it will pass the other gases. To do this thing, what we did, so this work we have done with collaboration with Saudi Aramco. And in this work, so I'll explain the motivation of this work. So if we want to use this MOF material in industry, so we need to make a column where the polluted gas will go in and pure gas will come out. Let's say this type of column. Okay, so this type of column where the polluted gas will go in and the pure gas will come out. And if what I have shown you before, these MOFs are powder material. So if you pack a column with full of powder material and you want to flow the gas, it will block. So the gas cannot pass through due to this highly dense packed material. So you need to make some space where the gas can pass through this column, but the carbon dioxide can be captured. So previously, people generally do the pelletization method. Pelletization, like the tablets we used to eat, that also made of pelletization. Means you make a powder material and put more pressure, it will be pellet. But we cannot use the technique for this MOF material, because as I told, it's a porous material. If you put more pressure, the pore collapses and the adsorption capability decreases. So we need to think about another technology where we can make pellet using this material so that we can use it in industry. So what we came up a new idea. So we choose a particular type of polymer materials as a binder. So that will bind this small particle and make a bead, and or tablet like a bead. And these beads can be used in the separation column. So here we use one of the highest capability CO2 capture MOF, that is NBOF5 nickel. That is, this MOF have very high tendency to capture the CO2 from even air. So what we did, we make a dough at first with the MOF powder, polymer, and then we give different shape. But we need to be careful that the amount of polymer and the MOF we are mixing, we need to use minimum amount of polymer so that the performance of this material, adsorption performance, doesn't go bad. But we need to be careful that it should not be so less that you just touch the bead, it will break down. It should be very hard. But the amount should be less. So what we did, we check the mechanical stability of this material, and we can see that it is very small. 1 centimeter cube material can hold nearly 1.5 kgs. And this technique we have used for a lot of different type of MOFs. And we have seen that our method is actually working for everywhere. And here we can see that not only the strength, the mechanical strength, these beads can stay in water or alcohol. So if you put in water or alcohol, the bead will remain same. But you can see the pallet, by pressing, we make some pellets, which we put in solvent, it breaks down. But so that you can wash and reuse. So that is the advantage of that. And also, then we use this material for gas separation purpose. We test what is the performance. And we make a column and we simulate the industrial gas by mixing the carbon dioxide, moisture, nitrogen, and we pass through our simulated system and the MOF column. And we got a very nice result, where you can see here in the graph 1, this is the time scale, and here in the beginning the nitrogen is going through, but the carbon dioxide is capturing. After 120 minutes, so when the column is full, all the material is full of CO2, then CO2 will come out slowly. So this is actually doing a very good saving of the CO2 over nitrogen. And here we can see we pass the humid gas, means what is in the industry, generally the gas comes out, it also contains water. And we have seen that in humid condition also this works very fine. And it's working for cycle to cycle. We can recycle it. So we can do so many times. So you can just capture and remove, capture and remove. So that works very fine. And one more interesting thing is that we compare the MOF powder as well as the MOF bead. And in case of MOF powder, we have seen that when we are trying to flow the gas, if we put 3 bar pressure, the upstream pressure means pressure from downside, the downstream pressure is 1 bar. But to get 1 bar downstream pressure, in case of bead, if we put 1.2 bar pressure, it can come out as a 1 bar pressure. So gas flow inside the column is very easy. So what we can conclude from our work is that these MOFs have the excellent CO2 capture properties, and this MOF can be made in bulk amount that can be used for industry. And this material are shaped with using the polymer binders, and their mechanical stability is very good. And the pressure drop, I told you pressure drop. So the gas flow happens very nicely. So is minimized using these beads. And the process was applied for all type of MOFs. So different types of metal organic frameworks are reported. We used nearly all type of MOF can be used using our technology or our method. So now I'll come to the next point, what you guys can do to solve this air pollution problem. So this is not only our responsibility to think, also you need to think what you can do. So first of all, be aware of air pollution and spread this awareness among others. If you nowadays, you just, internet is everywhere, every person, nearly a lot of people use. And so you search how to control this air pollution, and you will get a lot of knowledges and gain this knowledge and spread it. So, and what we can do, we need to stop the deforestation and we need to do the plantation. The plant are the main source where the CO2 can absorb and oxygen will come out to the nature. So if we want to lower the air pollution, we need to do the lot of plantation. So everybody can do that. And another thing is that we need to very, very careful about waste management, especially in India. The waste management system is not proper. We need to stop the crop burning. We need to reduce our plastic use. So if we use we can use it less amount of plastic, so that this plastic, when we want to dispose it, we want to burn a lot of the air pollution happens. And another thing is that we need to do the recycling of our daily waste. So especially we have 4 different type of waste, like paper waste, glass, plastic, metals. So that can be separately do the waste treatment, so that we can do it, we can do recycle. If we mix everything together, then there is no way of recycle. So we need to think about this to stop this air pollution. And we need to stop the fireworks during the New Year, Diwali, or any functions that create a lot of pollution. And we need to reduce the coal or wood burning during cooking. So cooking, for people should use the LPG gases, so that the pollution reduce and human health can be safe. And another thing we need to do is that we can do it every day, regulate the daily electricity consumption. The electricity production, energy production, creates a lot of pollution. So like in an empty room, we cannot let the fan or AC continue running. Or we can use the LED bulb, which consume less amount of electricity, so that instead of other normal bulb. So that we can consume electricity less. We can do that. And we can use the eco-friendly vehicle for transportation. Let's say for short distance, we can do cycling. That will be, our health will be better and pollution will be less. And the electric engine cars, that will also help to reduce this air pollution. And also we need to control the industrial pollution. Who are working in industry, they should follow the air pollution law. And at the end, the thing is that we need to raise our voice. We need to discuss about air pollution in social media or any seminar and everywhere. So this is actually, we are killing ourselves due to this air pollution. So raise your voice. So if anybody is violating the air pollution law, so protest against this and do the strong amendment of the air pollution law. And the next thing is that, who is the next? All the creature with the giant animal that died due to this means unbearable breathing condition. So to save our next generation, we need to come forward and be aware of air pollution and spread the awareness near to others and save your next generation. So this is the end of my presentation. I want to acknowledge my supervisors, Professor Rahul Banerjee and Professor Mohammad Eddaoudi and Professor Nobuhiro Yanai and Yusuf, who is mentoring during this work. And I want to put special thanks to Dr. Siad. He is my friend and colleague during the postdoc time, and he invited me for that's why I give him this lecture. And I also try to thank all the organizers, and especially principal ma'am and the HOD sir and all the IQSE coordinators and the organizers for this webinar. So thank you everyone, and all the viewers, thank you for listening this talk. Thank you.
Thank you, Arijit, for your good presentation. And here we have some questions, and some of them it was a little bit simple that I have answered here, but there are some other questions also available here. So I'm just reading. So can you hear it?
Yeah, I can hear you.
Okay, the first question is the principal from Mannaniya College of Arts and Science, and his question is the wood fire pollution will make disease?
Yes, of course, because wood fire will creates more amount of the particle, the pollutant particle, like the wood fire. When you will burn this wood, the carbon dioxide will happen, will come in the atmosphere, and the smoke come out, and smoke content lot of small pollutant particle that especially in if you remember in the village area, people used to cook with wood. The burning material they use as wood, and the lot of smoke comes, and the smoke really hampered their biological system. So it's really not a good technique.
So other question is from Gija, and her question is, what are the common type of MOFs are commonly used for CO2 capture? There has to be some optimum pore size for selective CO2 capture.
Yeah, it is a very interesting question. So it's a really interesting question. So the MOFs, the material is such like that you can control the pore size or pore volume. So by changing the linker length or metal ion, the coordination. So there is few factors that regulate the efficiency of carbon dioxide capture. So number one is that affinity. So carbon dioxide is somewhat polar than the nitrogen. So inside the MOF, if you create some centers which attract the carbon dioxide than other gases, then you can selectively take that carbon dioxide. And I'm coming to the pore size. There is a particular pore size. So if you see the kinetic diameter of the carbon dioxide, so is around 3.3, and this is very close to the nitrogen, around 3.8. So 3.3 to 3.6, the kinetic diameter of carbon dioxide, where the nitrogen is 3.8. So there is a little difference in the size. So there is some of the MOF where they can do the separation. So the pore size should be at around 4.5 angstrom, the pore size, where the nitrogen it cannot it just fit on the pore. So around 4 angstrom pore size. So the nitrogen cannot go in, but due to this variable kinetic diameter of carbon dioxide, it can be 3.3 or 3.6. So it can easily go inside the MOF channels and do the separation. And that is the technology in MOF. People are, one of the important technology people are using to capture the CO2 over nitrogen.
There is another question from Mohsina. Is MOF that much effective to CO2 capture?
Yes, nowadays people are, this is the one of the promising material people are trying. And as I told, our work is collaboration with the Aramco. Aramco is the world largest the oil and natural gas production company, and they are funding to do this research and go do more advancement on this topic.
So there is another question from Supriya. Sir, what is the adsorption efficiency of synthesized MOF in comparison with other material? Please mention its CO2 adsorption temperature.
So generally people, other material like porous zeolite people are generally use, or porous carbon, like the amorphous porous carbon, and some porous polymers. People are using other materials which are compared to these MOF. But they have different problem. Like the zeolites, or they bind CO2 so efficiently that the regeneration is problem. So it can absorb CO2, but regeneration is problem. Also the porous carbons, they are amorphous, so they doesn't have particular pore size. So the absorption efficiency is very less. The same thing is the porous polymer. So that's why the MOFs are more important in that cases, and the efficiency of MOF material with compared to others is high.
So there is an interesting question to you as an experimentalist. That question is from Ninu Krishna PU. Sir, computational chemistry can do something in this area?
Of course, the computational chemistry, of course, because whatever we are doing the test, before that we need to know, we need to have some idea that this will work or not. So in that case, the computational studies gives us the guide or the roadmap. So you should go in this way, not this way. So that is the first thing we need to do. Then the experimental hassle will reduce if we do the computational before we go to the experiment.
So there is another question from Ebin Sebastian. Since MOFs are also well known for their catalytic activity, what are the scopes of the simultaneous CO2 capture and conversion to fuel? Is the CO2 conversion possible on physics of the captured CO2? Is it possible to recycle and reuse the MOF after completing adsorption?
So at first I'll tell the recyclability. So as I shown in my work as well, the gas adsorbed in the MOF's surface, MOF pores, are physically adsorbed. It's not chemically binded. So so many times you can adsorb and dissolve by reducing the regulating pressure and temperature. That is called pressure swing adsorption and temperature swing adsorption. So you can swing the pressure and temperature, and you can recycle it. And so a lot of good MOF materials that are very stable MOF. So you can use it for a long time. And another question he asked about the what he asked about COF material that we can do catalysis. So so there was I have shown one slide, one reference, some ACS catalysis in my presentation. They actually did this type of work. So they tried to they make install a catalyst inside the MOF. So MOF have the metal part and organic part. In the organic part, they attach a catalyst, and this catalyst, their idea is that they first absorb this carbon dioxide and do the catalyst simultaneously. So the process, the first adsorption, and then convert this CO2 to other material can we also do. So it is obvious we can do that.
So other question is from Abdullah Kalandodan, and his question is, which MOF you used for CO2 capture? Did you do any modification in the parent MOF?
So the work I have shown here, we have used the nickel niobium F5 MOF. It's a well-known carbon dioxide captured for according to the till now, and this MOF is made of pyrazine, a small linker, and nickel and niobium as a metal center. And these MOFs we have used, and we didn't do any modification during MOF structure. What we did is that we did the modification in synthetic process. So initially, when material was synthesized in a small glass vial, but if we want to use this MOF in the industry, we need to make this MOF in kilos or tons. So in that case, we change the reaction, keeping the nearly same, but we change the reaction condition a little bit to grow or produce this MOF in bulk scale, like kilos, so that we can use it. And then we did other things like.
So there is other question from Smita SS. Sir, can we use graphene oxide composite based on copolymers for the effective absorption of CO2?
Graphene, the porous graphene people are using to absorb CO2, but the thing is that the porosity is not regulated when you will use graphene. Graphene are like flexible material, so and means layer material, and so the carbon dioxide need a particular pore size. So you cannot regulate the pore size with the graphene. But one interesting thing is that she told that the graphene and COF, so the covalent organic frameworks are also similar sheet-like structure. Means if you think about 2D COF. So some people have shown that if you mix this graphene and COF, they have good interaction, and the crystallinity of the COF material increase after adding graphene. So that will give you some hope, but it need more research. But my thing is, my answer is that it may have some difficulties.
So there is another question from Fasin. Is the same MOF can be bind CO2? It is not carbon dioxide, it is carbon monoxide.
Okay, the carbon monoxide is more smaller. So yes, the MOF can be used, the same MOF can be used to capture the CO as well. But there is some other MOFs which are more efficient towards CO. But this MOF can also absorb CO.
So there is other question from Dheeraj. Can we trap CO2 as a supercritical state in the solid material and store it for a long time?
This is an energy efficient process. Obviously, we can do that, but you need to spend a lot of money on that, and the industry will not try to do that. So that is the problem.
There is few questions more, maybe one or two. One question is from Akshay Babu. Can we condense the CO2 and liquefy it and use for the other purpose for reducing the pollution?
So as I told you before, that to put it in critical condition or in liquefied condition, you need to compress with high energy this carbon dioxide, and that require a lot of energy and power. So it's an energy efficient process. So people, industry don't want to do that.
So here is a last question for you. That is from Alfia Usman. It is a general question. So we know that coral reefs are important in determining the amount of CO2 in the atmosphere. How CO2 could be trapped by coral reef species?
So the coral reef are also one type of natural porous material, and they have the somewhat silicate or zeolite type of texture and carbonate type material, and they have a particular natural porous system. So they have the affinity to store the CO2. So especially it's a natural healing process.
So I think almost all the questions are finished. Thank you, Arijit, for your nice presentation. And I think I will give mic to my colleague and she will take the opportunity to say the thanks. And before the thanks, I just would like to inform the participant that definitely we will send you the participation, the attendance, the certificate that we will send you by mail, and also the feedback link also we will send you. So that will come immediately to your the corresponding mail ID. And now I'm handing over my mic to Dr. Shiji Fasil, who is the Assistant Professor and Department of Chemistry, and she will take this to say the opportunity to say the thanks.
Okay, thank you, Siasa. Good morning to all. Here we come to the end of our first webinar organized by the Department of Chemistry in association with IQAC. Here's a wonderful session delivered by Dr. Arijit Mallick, JSPS Fellow, Kyushu University, Japan. The session is very informative on the grounds of control of air pollution and the gas purification using the self-assembled metal organic frameworks. Also, there is a wonderful interactive session handled by Dr. Arijit Mallick. Dr. Arijit Mallick, thank you so much for your nice presentation and interactive session. On behalf of the Department of Chemistry and IQAC, I would like to thank all the participants present in the program. I extend my sincere thanks to our principal, Dr. P. Nasir, head of the department, Dr. Mercy Raj, and our IQAC coordinator, Dr. Dilshad, for the immense support and presence. Let me conclude. Thank you. Thank you all.
Thank you.
Okay.
Thank you. I think the session is finished. So now the session is over. Thank you very much for joining this program.